Okay, let's have a look at Newton's laws of gravitation and how we might apply them. So a few observations first. Newton said that every mass, or every object, attracts every other object in the universe. In other words, there's a force of attraction between them, and this force of attraction is known as the gravitational force, or in our case, Fg. Now, because the force of gravity acts over a distance, we can say that the force of gravity is an action at a distance force. So unlike me pushing this pen where I directly need to push it, gravity can act over a distance instead. The two objects don't need to be connected. Now, to set up the relationship between the force of gravity and our masses, we need to go through some thought exercises. So first of all, we say that force of gravity is proportional to the two masses involved. In other words, if I increase the mass of this object, or I double the mass of this object, then my force of gravity will be doubled as well. And the same thing with me. If I double my mass, then the force of gravity will also be doubled in relation to this pen as well. If I double both of these, so myself plus the pen, double that mass and double this mass, then my force of gravity will be 4 times greater. So our relationship between force of gravity and mass is that the force of gravity is proportional to the product of our first mass and our second mass. We said before that force of gravity is an action at a distance force, so therefore we should have some relationship between distance and force of gravity. So if we take a graph of force of gravity versus distance at a distance of 1 unit, and it can be any distance, we find that we might get a force of gravity equal to 1 unit on our y-axis. If we now double that distance, we find that our force is actually 1/4 of the size. If we triple the distance, we find that it's 1/9 of the original force, and if we quadruple the distance, it's 1/16 of the original force. So we can draw this line in, and that's a relatively common graph in maths, and it states that we have an inverse square relationship. So in other words, the relationship between the force of gravity and our distance is that Fg is proportional to 1 over d squared. Now if we combine these two relationships, we find that our force of gravity is proportional to the product of our masses over the distance squared between our objects. Not usable yet, but we need to somehow be able to rearrange this relationship by making it a usable equation. And to do that, we need to put a constant in there, and in this case it's the universal gravity constant, and we denote it with a capital G. And a force of gravity now becomes equal to this constant times mass 1 times mass 2 over the distance squared. A few things to note about this equation. First of all, that our G is equal to 6.67 by 10 to the minus 11 Newton meter squared per kilogram squared. And secondly, the distance between our two objects is always defined as the distance between the centre of those objects in a straight line. Now we can calculate the force of gravity, and we can do that quite easily by knowing the masses of M1 and M2 and the distance between the centres of those objects as well. But we're going to do something slightly different now. We're going to use this equation to calculate the acceleration due to gravity of an object moving toward a much larger object. So we've always been taught in our younger years of physics that F is going to equal ma. If we apply this to the force of gravity, then the force of gravity will always be equal to mg, where this m denotes the mass being acted upon by the force of gravity on Earth. So this tells us that G in this case must equal big G, our universal gravitation constant, times the mass of the Earth divided by the distance between the two objects. And in this case, because if we take me as an example, standing up on the planet Earth, my height is under 2 meters, so my radius is approximately 1 meter. The radius of the Earth, so to the center of the Earth, is much, much greater, so we don't need to take into account my radius. So essentially, as we'll look at down here, we don't need to worry about my radius. So we plug the numbers in. We've got 6.67 by 10 to the minus 11 for our g. We've got 5.974 by 10 to the 24th for the mass of the Earth in kilograms. We've got a radius of the Earth of 6.378 by 10 to the 6th meters. And this is where my meter, my radius, doesn't need to be counted because it's much smaller than this number here. So essentially this number hasn't changed. And obviously we've got to get the square of this distance between the centres of the objects, so we square the bottom. And if we work through this calculation, we find that we get a value of 9.81 metres per second squared, which is the acceleration due to gravity on the surface of the planet. Now we can also use this equation to find out the force of gravity at a distance above the surface as well. And to do that, we would have the radius of the planet Earth in this case, plus the altitude at which the object exists. And obviously we can go through that calculation. We're going to do it with acceleration due to gravity on Mount Everest. So once again, we'll use the same equation we had before. Big G, the mass of the Earth, the radius of the Earth, but this time we're going to add in the altitude of Mount Everest, which is approximately 9,000 metres. So our value for our distance between the centres of our objects now becomes 6.378 by 10 to the 6th plus 9,000 metres all squared. And we now find that our acceleration due to gravity has decreased to 9.71 metres per second squared. So this tells us as the objects are further and further apart, the acceleration due to gravity will decrease. And that's what we found from our previous notes. Now we can do one final thing with this particular equation. We can work out the ratio of acceleration due to gravity between two planets. So in this case, I've got planet Earth, and I've also got another generic planet. So acceleration due to gravity in the Earth is represented by g, mass of the Earth, radius of the Earth squared. The planet similarly is g, mass of the planet over r of the planet all squared. And if we want the ratio of Earth over that planet, we can rearrange these two equations to get the mass of the Earth times the radius of the planet all squared over the mass of the other planet times the radius of the Earth all squared. If we work through this calculation, this will give us a number. If it's greater than 1, it tells us the acceleration due to gravity on that planet is relatively higher than it is on Earth. And if it's less than planet Earth, then it'll have less gravitational acceleration due to gravity on that planet. So there's 3 examples of how we might also use Newton's law of gravitation.